This is the screencast for section 3.5, example 8. We're actually going to rewrite Newton's law of cooling in the following form. So we used to have, here's the before form, here's the after form. The only thing they did was subtract T sub m from both sides. So the temperature of the medium that was being added out in front, we subtract that from both sides. So now we get to use an exponential regression when we have data points. We wouldn't be able to use exponential regression in the form it took before because we would have this plus Tm that wouldn't be accounted for in an exponential regression the way our calculator does it. So remember, our calculator is going to put out y equals a times b to the x as our exponential regression. So if we look at Newton's law of cooling before, that would translate algebraically to capital T would be our y equals our a, the number in front of our base, would be T sub 0 minus T sub m. So this would be a. E to the negative kt, well, that would be our b to the x, because e to the negative k would then be raised to the t power. And then we're still stuck with T sub m. There's nowhere that our calculator can really put that. But if we change the way Newton's law of cooling is expressed, our y value can be T of t minus T sub m. And that will be equal to, a is still going to be, T sub 0. A is still going to be T sub 0 minus T sub m. And then e to the negative k would be our b to the, and then t would be our x. So this has a fit. That's why we have to subtract T sub m from both sides. So now we have to remember that our output values on our exponential regression are our final temperature minus the temperature of the medium. And then we'll be able to use the initial temperature minus the temperature of the medium as an exponent, within an exponential regression. So example 8, model Newton's law of cooling. In an experiment, a temperature probe connected to a calculator-based laboratory device was removed from a hot cup of coffee and placed in a glass of cold water. The first two columns of 3.23 here show the resulting data for time t in seconds since the probe was placed in the water, and temperature T in degrees Celsius. In the third column, the temperature data have been re-expressed by subtracting the temperature of the water, which was 4.5 degrees Celsius. So basically, time T and temperature T would be useful if we had a way to do a regression for the original setup of Newton's law of cooling, but since we don't, we had to subtract T sub m from both sides, and now our L1, our input values, our T values are going to stay the same, but our output values are going to be our final temperature minus the temperature of our medium. So I put L1, or T in L1, and I put capital T minus capital T sub m in L2. So we're going to kind of disregard the temperature for right now in our regression. Now part A asks to estimate the temperature of the coffee. So of course that would be the initial temperature of the coffee, because this coffee is sitting in air too, so it is cooling down. But we're really measuring the temperature of a probe in our data, so we want the temperature of the coffee, so the initial temperature of the probe. So as I said, in L1 I put my time t. In L2, I put capital T minus T sub m. So now I can create an exponential regression. I'm going to make sure my regression equation is stored into y1. And then I'm going to calculate. So this is the regression equation I get. Y equals a, so 66 times b, so 0.93 to the x. Now remember, our output values here represent capital T minus T sub m. So when I go to the graph, I turned on plot 1 and plotted my data points, as well as having my regression plugged into y1. So now I can see that the regression I made lines up with my data points, which is good. And it says to estimate the initial temperature of the coffee. So I'm going to hit trace, I don't want to be on my data point, so I'm going to hit up. I want to be on the actual regression equation I created. So I'm going to do 0, enter. So my initial would be 61.66, which of course is 61.66 times 0.93 to the 0. So making sure that all of my stuff is lining up. I am confident because of my data points and because of my exponential regression and plugging in 0 that 61.66 was the initial temperature in my exponential regression, not necessarily the initial temperature of my coffee, because remember, this y sub 0 in this case represents T minus T sub m. So T of 0 is what I'm trying to find. The initial temperature of the medium, remember, was 4.5. So I still need to add T sub m to both sides. So the temperature, the initial temperature of my coffee was 61.66 plus 4.5. So that's going to be 66.16 degrees Celsius. I would not be able to get that if I used my time in L1 and my temperature in L2, because I don't have a way in my calculator to create a regression that involves an exponential plus a constant. I only can do it with exponential with no plus a tm. So I had to kind of work the system a little bit and subtract t sub m from both sides to make sure that my output, and then acknowledge that my output was a subtraction of two things instead of just a plain old number. Part B, estimate the time when the temperature probe reading was 40 degrees Celsius. So when the temperature probe reading was 40 degrees Celsius. So again, I'm looking for when capital T was 40. So I'm looking for 40 minus T sub m equals the regression equation. I'm trying to find that T. 40 minus T sub m, well, that's 40 minus 4.5. So I can plug that into y2, which would be 35.5, and find the intersection. And I get that's about 7.36 seconds. Which makes sense because 7.36 seconds came from a plain old t value, not a t minus t sub m value. We added this to both sides, so now we're referring back to the temperature column. And 7.36 seconds, right smack in the middle of 5 and 10 seconds, would create a temperature smack in the middle of 31 and 49 degrees Celsius, which was 40 degrees Celsius, the temperature we were looking for. So now try problem number 51. Now that we know how this whole setup works and how to coordinate Newton's law of cooling with our calculator, this should go a lot more smooth. Or smoothly? I don't know. A thermometer is removed from a cup of coffee, again, and placed in a water with a temperature of 10 degrees Celsius, so slightly warmer than the last time. The data in table 3.24 were collected over the next 30 seconds. So we're going to draw a scatter plot of the data T minus T sub m. So I put the time in L1 and T minus T sub m in L2, and then had a scatter plot with zoom 9. Part B, find an exponential regression equation for the T minus T sub m data. So in other words, this is our output. Superimpose its graph on the scatter plot. So after forming the exponential regression with my calculator using L1 and L2 and putting it into Y1, I can see that the regression lines up very well with the data points. My official equation would be y equals, or t, actually the directions ask us for T minus T sub m data, so I'm going to put T minus T sub m equals, which was our y, 79.47 times 0.93 to the t. And then part C asks us to estimate the thermometer reading when it was removed from the coffee. So if the thermometer was removed from the coffee, that was at the very beginning. So we want to know what the initial temperature of the coffee and thermometer was. So I can plug 0 in for T, which gives us 79.47. That would also be our initial temperature on the calculator. But remember, that does not represent the initial temperature of the coffee. That is the initial temperature of the coffee minus the temperature of the water. Now the temperature of the water was 10 degrees Celsius, so T minus 10 would equal 79.47. So if I add 10 to both sides, I get 89.47 degrees Celsius for the initial temperature of the thermometer and the coffee, because they would both have been the same temperature as the beginning of this process started.